Here we have a line. We'd like to know the length of that line. If we can break the line into a bunch of small segments and determine the length of each segment, then the total length of the line is the sum of all of those small segments. We can find the exact length of that line in a similar way if we will imagine dividing the line into smaller segments. The smallest possible segment we can imagine is the differential length dl. Then we can add up all of those tiny segments through integration to find the exact length of the line. We have some function, y is a function of x, and we want to determine this area. We can imagine a bunch of rectangles, each of height y and width delta x. The area of each rectangle is y delta x, and the sum of all of those small areas will be a good approximation for the total area. More rectangles with smaller delta x will make the area approximation even better. If we make each rectangle even smaller, as small as we can possibly imagine, the width becomes dx, the height is still y, and then y times dx is dA, or differential area, smallest we can imagine. The exact area is the integral of dA, or the integral of y dx. Now determine the volume of an object. Here's a 3D solid horn-like object. Here's a side view, and the boundary is at y of x. Slice through the horn tiny discs of thickness delta x and radius y of x. The volume's pi y squared delta x. Total volume approximation is the sum of all of the tiny disk volumes. If we make the disks as small as we can imagine, give them a thickness dx, the differential volume is pi y squared dx. The exact volume is the integral of the differential volume. And the exact volume becomes the integral of pi y squared dx.